Hello students, welcome back. Let us resume our discussion in section 4. We completed 4.1 and 4.2, and now let's go to 4.3. 4.3 is actually a stronger version of 4.2. Do you see that? Well, you can certainly see that the conditions are the same. M is the order of the original, and Q is the order of the subgroup. Then Q is M over D, as I highlighted here, where D is the greatest common divisor of M and S. M is the order of the original cyclic group, and S is the power of the generator of the subgroup. So M comes from the original, and S comes from the subgroup. Is this a stronger version of this? Do you see that? Well, I hope at least you see one of the two. Q divides M, which actually means M is some integer times Q, versus this one here. That integer is actually D, the GCD of M and S. So this one down here is a stronger version of the second conclusion of 4.2. So this bold here is a stronger version of this bold. That much is certain. As for the first conclusion here, it's not that obvious, but surprisingly it may be that 2 comes from 4.3. Let me show you. Before proving 4.3, let's make this remark. 4.3 is actually a stronger version of 4.2, and then we can prove that the second conclusion of 4.2 follows from the conclusion of 4.3 like this easily. Q is M over D, so flip this denominator to the other side, you get Q times some integer is M. That integer is D. Great. How about the first conclusion here? Well, Q is M over D, so dQ is M, so far so good. And then here we make some interesting observation. This D is equal to S over C, which is an integer, because D divides S. Does it make sense? Well, D is a GCD, so it's a common divisor of M and S, so D divides M, and also D divides S. Therefore, S over D should be an integer. Let's say that integer is C. Then D is S over C. And that's an integer. And that's right here in place of D. So that was a bit tricky observation, but what follows next is rather obvious. Now that we have this, flip the denominator to the other side, then we get SQ is equal to CM. So we got M times a certain integer is SQ, therefore M divides SQ. Conclusion: 4.2 comes from 4.3. The conclusion of 4.2 comes from the conclusion of 4.3. So this is a stronger version of 4.2. That's interesting. Then why did it consider 4.2 to begin with? I mean, this is a stronger version. Why did it consider the weaker version to begin with? The reason is, in order to prove this stronger version, we're going to need this weaker version as a stepping stone. So we're going to use 4.2 to prove 4.3. That's why we did 4.2 beforehand. Okay, now let's go ahead and prove 4.3. And we're going to do it in 3 steps, basically. Step 1, we're going to work out the property of GCD. And then we're going to do this. Q divides m over d, and m over d divides q. That's what you're going to prove. And therefore, they're equal. That's what you're going to do. By the way, in general, if one integer divides the other integer and vice versa, it doesn't mean they're equal. They may have two opposite signs, but in this case it's okay because q and d, they're all positive. M is the order, q is the order, so they're positive. And then d is GCD, that too is positive, so they're all positive, so yes, okay. This one follows actually. Okay, that's the plan. Let's go to step 1. Let's work out the property of GCD. D is GCD, so it's a positive integer so that it's a common divisor, so it divides m and also it divides s. And finally, it's the greatest common divisor, and that corresponds to this linear combination property, these um plus vs, where u and v are integers. Do you recall this from the definition of GCD from lesson 3? There, I used non-negative integer or whole number w, not z plus. Here I'm using z plus. The reason is because we are considering non-trivial. M is positive, q is positive, so GCD is not going to be 0. GCD of 0, 0, then that's 0, but that's not the case, so z is positive. So strictly positive. So a little bit different from the definition of GCD that we considered in lesson 3. Common divisor, yeah, that's the same. And then linear combination, that's the same. Okay, all right. Now that we got GCD, let's prove the first divisibility. We'll prove that q divides m over d like this. A to the s power has order q. Remember this? Green. That's a subgroup. And then let's consider this computation. Maybe I should expand the fonts just a little bit. A to the s power to the m over d power. Yes, that's an integer because d divides m, so m over d is an integer. And then if you use the exponent rule, we just have multiplication of all those powers, and the multiplication is commutative, so you can multiply m before s. So we have a to the n power to the s over d power. And what is a to the n power? That's e, isn't it? Because the order of the original is m. And also s over d power, that's integer power. So everything is well defined and we have e. So a to the s power to the m over d power is equal to e. And a to the s power has order q. So a to the s power, this thing, which I just highlighted in green, to this power is equal to e. That means that's divisible by its order. Remember this? Generator to a certain power is e, then that power is divisible by the order. That's what I did. So q divides m over d, and one down, one more to go. Okay? A to the s power to the m over d power can be manipulated like this. A to the m power, which is e, and e to the s over d power, and s over d is an integer power, so well defined, so we get e. So we don't have any radical or anything like that. So if you have rational power, then no good. We have to have integer power. Okay, so much for the first divisibility. Now let's go to the next divisibility. And we'll use the fact that A has order m and a to the s power has order q. And we're going to start from here. A to the dq power, again, let's expand the font so that we can see those exponents better. A to the dq power, and d is um plus vs form because d is gcd. Do you see that? We just use this. And that's the q power. So what is it? That's a to the um power times a to the vs power. That's it, isn't it? And what is this? A to the um power. A to the m power is e because a has order m. So this whole thing is e times a to the vs power to the q power. So we can drop out this e, but then again, what do you do next? Well, that's what we do. We get up to here, so we just use that's e, we just use that, so we can drop it out. And then using the exponent rule, this is just multiplication, so we can change the order of multiplication. You can write a to the s power to the q power, but that's e. Because this subgroup has order q. Remember this? So that's e. So a to this power is e. So the order m divides dq. We're almost there. This gives me the desired conclusion. M over d divides q. Why? Because m divides dq means dq is some integer times m. Now from here, if you divide d away, then q is that integer times m over d. Consequently, the m over d divides q. That's the second divisibility. So put those two together, we have the desired equality. Q is indeed equal to m over d. So the conclusion? Well, here we go. And as for the application of 4.3, I assigned several homework problems associated to this. So there's some computation involved with this one. That's going to keep you busy. And the final topic here, they're all isomorphic to Zm. And for this one, again, I'm going to give you just a hint, a sketch, and then I'm going to ask you to complete this. Basically, we can define a map from this cyclic group to Zm, where m is the order of this cyclic group, like this, a to the nth power as n bar. And then you have to prove these two. Is phi an isomorphism? In other words, does it preserve the group operation? The group operation in G, the cyclic group, versus the group operation for Zm. So addition modulo m, you have to check that. And then 1 to 1 and on to. If yes and yes, and they are isomorphic, so essentially we are looking at the same group. So eventually everything becomes very, very simple. But of course, you have to check all those steps and then make sure everything is right before actually getting there. Oh, great. That completes lesson 4.